Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the optimization of the regenerative Brayton cycle. When a Brayton cycle does not operate at the condition of maximum specific cycle network, the temperature of the exhaust gas leaving the turbine is often considerably higher than the temperature of the air leaving the compressor. Therefore, the high-pressure air leaving the compressor can be heated by transferring heat from the hot exhaust gases in a counterflow heat exchanger, which is also known as a regenerator or a recuperator. The thermal efficiency of the Brayton cycle increases as a result of regeneration, since the portion of energy of the exhaust gases that is normally rejected to the surroundings is now used to preheat the air entering the combustion chamber. This, in turn, decreases the heat input requirements for the same network output. Note, however, that the use of a regenerator is recommended only when the turbine exhaust temperature is higher than the compressor exit temperature. Otherwise, heat will flow in the reverse direction, decreasing the efficiency. This situation is encountered in gas turbine engines operating at very high pressure ratios. Let's check the heat addition and the heat rejection. By definition, we have: based on the process, the temperature for each state is. Look at this expression of the cyclic specific network for the Brayton cycle with regenerator, equation 1066. It has nothing to do with the regeneration effectiveness F. This means the cyclic specific network is not affected by the regeneration, only depends on the pressure ratio. However, the thermal efficiency will be influenced by the regeneration. Therefore, the thermal efficiency by definition then is: for the fixed regeneration effectiveness T1 and T3, the efficiency depends only on T2, and then the optimum pressure ratio can be obtained. Rearranging the thermal efficiency equation 1067 and differentiating yield. Setting the first order derivative, which we just obtained, to 0, the most economic compression end temperature corresponding to the maximum thermal efficiency is. The most economical pressure ratio at the maximum thermal efficiency is. Under the cold air standard assumptions, we found the optimum pressure ratio depends on the regeneration effectiveness T1 and T3. The actual gas turbine cycle differs from the ideal Brayton cycle on several accounts. For one thing, some pressure drop during the heat addition and heat rejection process is inevitable. More importantly, the actual work input to the compressor is more, and the actual work output from the turbine is less because of irreversibilities. The deviation of actual compressor and turbine behavior from the idealized isentropic behavior can be accurately accounted for by utilizing the isentropic efficiencies of the turbine and compressor. The detailed analysis for an actual gas turbine cycle with no regenerator or recuperator can be found in the example 10.8 of the textbook. Okay, that's all for this task. Thank you very much, and see you next time.